Hello, Science 20s. Our lesson today is going to be on Newton's second law and impulse. Newton's second law states that an object will accelerate in the direction of the net force applied to the object. So again, we're going to be looking at net force. So if that means we have to add together the force applied and the force of friction, we can do that. But that means that we're going to be also looking at mass and acceleration. So what I want to do is remind you of the units for these. So force is again going to be measured in newtons. Mass is again going to be measured in kilograms, and acceleration is meters per second squared. I will point out that acceleration will be a vector quantity, and force will also be a vector quantity. So when we think about this, I really want us to think about, and if that means pulling out our data booklet and having the formula sitting in front of us, what factors influence the rate of acceleration? So if I'm going with what I just saw there, I know force plays a role, I know mass plays a role. So here is my formula that I have in my data booklet. Well, if I want to determine what factors affect acceleration, let's get acceleration by itself. So when we go across the equal sign, we're going to go to a different floor. So my formula is going to be acceleration equals net force over mass. So the factors we have to take into account when we're talking about acceleration is the total force that being supplied and the mass of the object. Think about it. When a force is being supplied, the mass is going to determine how much it can accelerate. Bigger objects will need a bigger force to accelerate as much. Well, let's try a couple examples. As always, copy down the example. Let's make a list of variables down the side. Then, if you're feeling comfortable, go off with your calculator and let's do the calculation. So, in the question, a golf ball has a mass of 0.45 kilograms and is struck by Scooby-Doo, giving the ball an acceleration of 1.9 meters per second squared forward. So let's make forward positive. What is the net force applied to this golf ball? Assume friction is zero. So we're going to assume no friction in this, no wind resistance, no friction of the golf ball in the ground. So we're going to make this quite easy. Well, again, we have our formula from our data booklet. F net equals mass times acceleration. So we're going to take 0.45 kilograms times by positive 1.9 meters per second squared. So decimal 45 times 1.9, enter. And my force net is going to be positive 0.86 newtons. Again, you can put it in newtons because it's a force, or you can keep the units that you have here, and you could have positive 0.86 kilogram dot meters per second squared. Either units would work for this. Okay, please copy the question, try this one for yourself, and then unpause the video to check your answer. So it tells me an H3 Hummer with a mass of, oh, I goofed it. I changed the question. I grabbed the wrong pen. Okay, let's go back. So my mass of 1,250 kilograms is traveling 45 kilometers per hour east when the driver engages the brakes to stop at an intersection. If the net force is 7,000 newtons. So we are traveling east, our force is west. So I'm going to make this negative because normally when we do this, west is negative, east is positive. So I'm going to make that negative for this. And we would like to determine the magnitude and direction. So we would like to get our numerical answer for the deceleration. So that's going to be our negative acceleration. So again, our formula is F net equals mass times acceleration. If I'm solving for acceleration, mass is going to go down. So acceleration equals F net divided by mass. So I have negative 7,000 newtons divided by 1,250 kilograms. Negative 7,000 divided by 1,250. And my answer is negative 5.6. And acceleration is going to be in meters per second squared. Again, if you forget the unit for acceleration, please come to your data booklet. They tell you the variables as well as the units. So if you've forgotten or you go, is this supposed to be in grams or kilograms? Please look on your data booklet. It gives you a lot of extra, very, very good information. By the way, this negative value means that our acceleration was moving west because we decided west was negative. Okay, let's try another example. Determine the acceleration of the following vehicles. So we've got acceleration. Let the direction of the applied force be positive. So the engine of a motorcycle supplies an applied force. So it said applied force is going to be positive. So this is going to be force applied. And that in our book is abbreviated with an A, but I might write applied just so we don't get confused. And we said it's going to be positive, so 1,880 newtons west to overcome frictional forces. So that's force of friction. And again, in your data booklet, that's FF. I'm going to write friction because this way everybody understands me. So it's going to be applied east. So that's going to be a negative 520 newtons. And normally we would say east is positive, west is negative. However, they told me in here the applied force is going to be positive. And this is my applied force. So it's positive. They also told me that the rider and motorcycle has a mass total of 245 kilograms. So the first thing I need to do is there's only one formula for force applied and force of friction, and that is to find force net. So we're going to add force applied plus force of friction. So I'm going to add positive 1,880 newtons plus a negative 520 newtons. And get a positive 1,360 newtons. And because it's positive, that is moving west. Secondly, it says, hey, find acceleration. Well, we know F net equals mass times acceleration. So we're going to solve for acceleration is F net over mass. So I'm going to take positive 1,360 newtons divided by 245 kilograms. And my value works out to be positive 5.5 meters per second squared. And again, 5.55 is also an acceptable answer. So to change the momentum of an object. So we're trying to get into this momentum thing. This is so not important on a day-to-day thing, but I don't want you to just go, hey, where did another formula come from? So I'm going to take the formulas in your data booklet, so ones that you know, and I'm going to go ahead and start adding them together to show you how this other formula in your data booklet was actually determined. So if we think about this, it says to change the momentum of an object, the mass, the velocity, or both of those things must change. If the mass remains the same, then it must be the velocity that changes. Therefore, acceleration occurs because, right, velocity is either going to speed up or slow down. That's going to be some sort of positive or negative acceleration. And the reason we don't change mass a lot is, right, we pick an object like a car. A car has a mass. It's not going to gain mass in the middle of an example. So when I think about doing this, I have force equals mass times acceleration. Now, I want to remind us that in previous lessons, we've seen that acceleration is actually VF minus VI divided by change in time. So if I was to now sub this in place of A, I would have the new formula of force equals mass times VF minus VI divided by time. Therefore, if I'm going to, because I'm going to multiply these, multiply mass all the way through. And then, of course, time is still on the bottom. Now, I want to remind us the definition of when you multiply mass times speed, that's momentum. So remember, P equals mv. So I can take this idea and I can say, well, since P equals mv, I can substitute this in as the final momentum minus P equals mv again. This is going to be my initial momentum. And then I can divide it by time. And so if I shorten this formula up, I can say, well, force or net force is equal to a change in momentum over a change in time. Well, that should make sense based on what we've seen in our data booklet. Because I think you've seen on the formula sheet, the formula where, hey, momentum is, right? Force times time. So this is a formula you're familiar with. So again, a little bit of math just to show you where formulas come from. Not important enough that you have to actually be able to keep doing it. So I would like to look at a barn owl. And that's a perfect example because I always keep saying, for instance, when an owl actually does something, he does not change mass. So his mass is the same. So my owl has a mass of 2.1 kilograms, flying at a velocity of, so that means his initial velocity was 15 meters per second. Since it's east, I'm going to make that positive. And it strikes head on the windshield of Brandon's car, traveling at 30 meters per second. So Brandon's car is traveling at 30 meters per second. And because it's traveling west, I made it negative. If the time interval of this collision was 6.7 times 10 to the negative 3 seconds, I would like to know what the force is. Now, if I look at my data booklet, I have a formula for this. Force equals mass times final velocity minus initial velocity over a change in time. So I am going to take 2.1 kilograms and I'm going to multiply it by negative 30 meters per second minus a positive 15 meters per second, and then divide the whole thing by 6.7 times 10 to the negative 3 seconds. So here's how I would type it in my calculator. I would go 2.1 bracket negative 30 minus 15 close bracket enter divided by 6.7 times 10 to the raised negative 3. And my answer I'm going to get is going to be, so my answer I'm going to get is negative 1.4 times 10 to the 1, 2, 3, 4 kilograms dot meters per second squared, or negative 1.4 times 10 to the 4 newtons for my bar mountain. Now, in our driving example here, we have two scenarios where on the first car, car A has time. They're both traveling 100 kilometers per hour, but they have time to slow down to stop. Where in the second example, he's traveling at 100 kilometers per hour and he has no time to slow down to stop. So it's not a gradual stop. He runs into a brick wall. So the force experienced will decrease if change in momentum occurs over a longer period of time. So the longer this period of time is to slow down, the smaller the force experience is going to be. If you've ever driven in a car, if you slow down with lots of notice, right, you'd barely even feel yourself slowing down or going forward. The moment you slow down quickly, right, you jerk forward and jerk backwards, and you shake up everybody in the car. I think the idea of momentum is quite easy to understand. So what I would like to do is last two questions. I'm going to do the same example twice, but what I'm going to do is I want to change the seconds. So we are trying to find what force is involved in stopping a massed vehicle of 1,200 kilograms traveling at 28 meters per second. So that's going to be my change in velocity is negative 28 meters per second. And my time is going to be 25 seconds. So we take 25 seconds to slow down, to apply, right, friction, the reverse force to slow us down. Well, we have force equals mass times change in velocity over change in time. So we have 1,200 kilogram car times negative 28 meters per second divided by 25 seconds. My answer is negative 1,344 newtons. Now, what I would like to do is, let's do the question again, but instead of 25 seconds, let's do it with 5 seconds. So instead of typing in 25, we're going to do 5 seconds instead. So again, we're going to have 1,200 times negative 28 meters per second divided by 5 seconds. This time you're going to find that the F net is going to be negative 6,720 newtons. When we have a much suddener stop, 5 seconds to slam on the brakes, we have a much larger force than when we had 25 seconds, 5 times more. We had a significant reduction by 5 times the amount of force that's going to be transferred on your body, on your animals, on kids in the car, on seniors in the car, all those other items.